Welcome to our deep dive into GPU warp divergence. Understanding this concept is crucial for writing efficient GPU code. In the SIMT execution model, threads are grouped into warps of 32 threads each. These threads execute the same instruction simultaneously. Here's a simple vector addition. All 32 threads execute this exact same instruction on different data elements. When all threads follow the same path, we achieve perfect synchronization and 100% efficiency. This is the ideal scenario. But what happens when threads need to take different paths? Let's examine conditional branch divergence. Consider this if-else statement. Some threads satisfy the condition, others don't. In this example, threads alternate between two paths. Path A threads are shown in blue, path B in orange. Here's the problem. The hardware must serialize execution. First, it executes path A while masking path B threads. Then it switches. Path B executes while path A threads are masked. The second type of divergence occurs with variable loop iterations. Each thread has a different work count, leading to different numbers of loop iterations. Notice the color gradient. Green indicates low iteration counts, yellow medium, and red indicates high workload. This legend shows the workload distribution across our threads. Threads within a warp execute in lockstep. When different threads have different numbers of loop iterations, some threads finish earlier than others. However, these early finishing threads cannot exit immediately and remain inactive. Execution must continue until the thread with the longest running loop completes, which reduces overall parallel efficiency. Dynamic function calls create a third divergence type. This switch statement calls different functions based on thread-specific data. Here we have three operation types distributed across threads: add in blue, multiply in orange, and divide in purple. The hardware serializes this into three execution phases, one for each unique function call. Efficiency drops to roughly 33%. Let's quantify the performance impact across different divergence scenarios. No divergence gives us 100% efficiency. A 50-50 split cuts that in half. Four-way divergence drops us to 25%. Worst case, one thread per path delivers only 3% efficiency. The key insight: efficiency is inversely proportional to the number of unique execution paths. Now let's explore mitigation strategies. First up, data sorting. At scale, unsorted data leads to warps being populated with heterogeneous work. By globally sorting work items before execution, similar tasks are assigned to the same warps. After global sorting, adjacent threads operate on similar data, producing coherent warps. Warps now execute with uniform control flow, effectively eliminating intra-warp divergence. Sorting reduces masked execution and improves memory coalescing. The trade-off is the global sorting overhead, which may not be worthwhile for small workloads. Our second strategy is predication, executing both paths but masking results. Here's our branching code that causes divergence. We transform it by removing the branch entirely. Both computations happen for all threads. A mask then selects the correct result. No branching means no divergence. All threads execute together in perfect lockstep. 100% utilization achieved. The benefits are clear. Zero divergence for simple operations. However, we waste computation on false paths. This approach only makes sense when branches are cheap. Strategy 3 focuses on load balancing across threads. This imbalanced workload creates a severe bottleneck. Some threads finish quickly while others labor on. We redistribute work to achieve uniform load across all threads. Now every thread has similar work. No thread sits idle waiting for a straggler. Techniques include work stealing, where idle threads take tasks from busy ones, dynamic scheduling for runtime assignment, and chunked iteration patterns. Sometimes, the best solution is rethinking your algorithm entirely. Consider atomic histogram computation. The naive approach uses many branches, one per bin. By using computed indexing instead of conditionals, we eliminate all branches. One clean path for all threads. Key principles. Prefer branch-free computations. Use arithmetic over conditionals. Leverage data parallel patterns. And consider multi-pass algorithms when single pass creates divergence. Let's consolidate our knowledge into actionable best practices. 1. Profile first to identify actual hotspots. 2. Sort data to group similar work. 3. Use predication for simple conditionals. 4. Balance load across threads. 5. Redesign algorithms to avoid divergence fundamentally. Remember, prevention is better than cure. Design for divergence avoidance from the start. Let's wrap up with our key takeaways. Divergence serializes execution, reducing GPU utilization. It manifests in multiple forms: conditional branches, variable loops, and dynamic function calls. Mitigation requires deliberate, thoughtful design choices. And profile-guided optimization is essential for finding and fixing real bottlenecks. The most important lesson: write GPU-friendly code from the very beginning. Design with warp-level thinking, and you'll achieve the performance GPUs are capable of delivering. Thank you for watching.